Section 8-4 is on the volume of a solid of a revolution by cylindrical shells. The objective of this section is to find the volume of a solid of revolution by slicing into cylindrical shells. So let's take a look at another example here. Example 2 says, let R be the region bounded below by the graph y equals x to the 1/2. Let's go ahead and write these equations down. So it's below by that graph, y equals x to the 1/2. Above by the graph, y equals 2. And on the left by the graph, y equals x. And we're going to rotate this. It says find the volume of the solid generated when R is rotated about the line y equals -1. So we're rotating this around the line y equals -1, the horizontal line y equals -1. Assume x and y are in feet and then show that your answer is reasonable. Okay, so let's first sketch the region that they're talking about. You can use your calculator to help you sketch this if you need to, but I think we can sketch this without our calculator. We'll see how well we do here. So let's say that this is our x-axis, and the square root function, we know, is a function that kind of looks like this, and the line y equals 2, that's a horizontal line right there at 2, and then the line y equals x actually would look kind of like this. All right, so there's our 3 functions they gave us, and we're rotating this around the line y equals -1. So y equals -1 we'll say is right here. So this will be at -1, so we're rotating around that axis there. So it's a horizontal axis that we're rotating around. Okay, so the region that we're looking at here then, I guess first of all to mark that, it said it was bounded below by the square root function, above by the line y equals 2, and on the left by the line y equals x. So that's the little triangular region that we're looking at. So if we're going to use the shell method says to draw a slice parallel to my axis of rotation. So my axis of rotation is horizontal. So my slice is going to be horizontal. So we'll draw a slice in there. Notice that one slice does represent all the slices. It goes from the curve on the right to the straight line on the left. And we'll name these 2 points here, the endpoints here. So we'll call this one x1y on the left side, and we'll call this one x2y on the right side. All right. And now I want to rotate that around the line y equals -1. And again, I'm going to try to sketch what this looks like when we rotate it around that axis. Certainly look in your book there. They'll give you definitely a better sketch than probably what I'm going to give you here, but it's going to be, I'm going to try to give you an accurate sketch. But when I rotate this around, we're going to end up with something that looks like this. Oops, I should have a vertical side there. And it has a thickness to it, so it looks something like this and like this. Okay, again, it's just the shell, so it's hollow in the center there. And we want to take that shell, we want to slice it and then unroll it. So when we do so, we're going to end up with a long, thin, narrow slice that looks something like this. All right. And again, the dimensions of this slice, this vertical distance, or actually it's horizontal distance that we have right here. I'll mark that right here in green. Actually, I probably should do that in a different color. Let me mark it in red there so it's easier to see. That right there corresponds to this distance right here. Those two are the same. Which that right there is a difference in the x values. It's going to be x2 minus x1. So go ahead and mark that. And then this guy right here, which was the circumference of this circle, becomes now the length of this slice when we slice it and unroll it. So that is equal to 2 pi times my radius, which my radius is now this distance right here. This is my radius. It's a difference in those y values. So it's the y value on the top minus a -1 at the bottom. So it's y minus a -1. In fact, I'm going to write it that way just so we see where that comes from. So it's not just y, because we are rotating around y equals -1. It's y minus a -1. And then the thickness of our slice initially, this thickness right here of this slice, that's a small change in y, so we call that dy. So I'll mark that over here that this thickness here is dy. All right, so now we want to find the volume of this. So we call it dv. And again, dv is going to be the volume of that rectangular solid, length times width times height. So the length of it is 2 pi times, I'm going to write it as y plus 1, y minus a negative 1, times the width, which is the x2 minus x1, times the thickness, which is dy. So there's our equation of this volume of this one slice, this one shell. And now I want to get this in terms of one variable over on the right side. The fact that I have a dy tells me I want to get this in terms of y. So we'll keep the y plus 1 in there. And now for x2, go back up to your graph and check out where x2 is at. x2 is on the curve there. That's the square root function. So I need to find out what x is equal to. So if I know y is equal to x to the 1/2, I can solve for x. I'll just write that up here underneath this equation here. Solving this for x, squaring both sides will give me that y squared is equal to x. So x2 is equal to y squared. So I'll replace x2 with y squared. And then minus x1. x1 now is on the straight line there, the linear function. That was just y equals x. I guess technically I have to solve that for x, but it already is solved for x. So I can just replace x with y times dy. And once we get this in terms of just one variable, we can now integrate this thing. Again, we have a differential equation. The way we solve a differential equation is through integration. All right, there is our differential equation. We're going to integrate both sides of this. I just need limits of integration. So over on the right side there, this is in terms of y, so I got to find y values here. So I just have to think about how far down and how far up do I want this slice to go. The top part of that's the easy part. The bottom part is the bottom of this little triangular region that we have there. So I need to find out where that intersection is. That's the intersection of the square root function and y equals x. So I got to find out where those intersect. I can just fit that in right here. If I take x to the 1/2 and I set the, oops, I should use the other equation though. I want a y value here. So instead of x to the 1/2, I'll use the x equals y squared. So I take y squared and set it equal to the x equals y. So set those two equal to each other. Just replace the x's there with each with the other equation, and solve this now for my y value. So if I take y squared and subtract the y here, I'll get y squared minus y equals 0. Factor out the y, and I'll get y times y minus 1 equals 0. So my two solutions actually are at 0 and at 1. The first solution down here at 0 I really don't need. The second solution is up here at 1. That's the one that I want. So it looks like my limits of integration go from 1 to 2. Now again, you can use your calculator to help you find those intersection points. There's lots of ways you can do that. But there it turns out to be our function that we want to integrate. So v turns out to be equal to the following. Now I know they said to use fundamental theorem, and you can certainly use that here if you want to. I'm not going to require that you do that. I'm going to consider this enough work just getting the equation set up. And so certainly practice that on a couple of these if you need to, but I'm going to go back to my calculator and actually have it help me integrate this thing. Oops, let me move this down so I can see that equation. So let's just go to our calculator and do some numerical integration. So under your math menu, we'll do FNINT of 2 pi times y plus 1. Now I'm going to leave this in terms of y. You could easily just put this in terms of x though. Oops. Y plus 1 times y squared minus y. It would just save you a few keystrokes there. Instead of having to hit alpha y to do this, you just hit your x key to do it. And if I put this in terms of y, then my variable is y. I have to indicate there. And I'm integrating from 1 to 2. And we get 14.137. Again, if you want to see if that's a nice multiple of pi, you can divide that by pi. And we get 4.5 pi. So our volume turns out to be 4.5 pi. And they said that we should assume that this is in feet. Assume that x and y are in feet. So if this is a volume, then this would be in cubic feet. So we get 4.5 pi cubic feet. All right, that's as far as we need to go for the second half here.